This video is part 2 of a multi-part series in which we're looking at multi-technology design. In part 1, we looked at some of the problems with multi-technology design and how the AWR design environment, because of its architecture and feature set, allows you to cut through some of the shortcomings of these flows. In part 2, we'll review what we went over in part 1, as well as look at the AWR design environment as to how we would actually set up a multi-technology design. In traditional module design, multiple tools are necessary to design in these technologies or in these flows, because no one tool set's able to span all the necessary areas. In other words, some tools are optimized for IC simulation, some are optimized for PCB layout, and so we need to combine all these tools in a very EDA intensive effort to create a flow which is going to be useful. Moreover, because there's actually no PCB module design step being done, in other words, the module is viewed more as a mechanical integration technology than an electrical design one, we often leave the actual electrical analysis or electrical design to an analysis step post layout. What this does is it really takes away the ability to do parametric design, optimization, tuning from the electrical engineer and forces him to go into more of an analysis mode, which leads to many iterations in time-consuming EM, which ultimately lead to multiple iterations of the design itself. The AWR design environment gets around this because, unlike other EDA tools which have a different database for every view of the design, schematic, layout, analysis, and so forth, and a different database for every technology in the design, including you may have multiple databases for different ICs, it makes it really difficult to integrate these things. In the AWR design environment, we have one unified data model, which is not only able to capture in that single data model the schematic, the layout, the simulation, the extraction, for a technology, but it's also able to do this for all the technologies. They can all be simultaneously loaded. So not only can you co-simulate HBT, PHEMT, silicon, module at the circuit or system level, but you can also co-layout, co-verify. You can look at the design in its constituent parts or as one integrated whole. And this really allows you to design within the context of the entire module, not just the bits and pieces. At the layout level, we don't need to reduce our die to pretty picture GDS2 rep cells. We can actually reach down into those die and manipulate them in the context of the overall design. So we can make trade-offs that are very key in terms of space, cost, as well as electrical performance. This allows us to really have a very flexible flow where we can either individually design MMIC or RFICs, packages, or boards, but then we can also think about integrating them and co-designing them together as their constituent parts, or as black boxes where we really don't go inside and touch them, but we have that flexibility to load this the entire module in all its complexity into the design environment and be able to make trade-offs at whatever level necessary. What we're going to do now is we're going to change gears and actually go into the AWR design environment and talk about how we would set up a project to do a design very similar to this, where we may load multiple die like a gallium arsenide PHEMT and a silicon SiGe with a multi-layer module laminate where we can integrate passives and have interconnects, wire bonds connecting the two, the die to the module, or flip chip technology as well. So let's go over to the AWR design environment and see how we do this. I've set up this project already to have a module technology. This is a multi-layer module technology where I've also got some passive structures, some SMT passives. Here's what the layer stack up looks like. It's basically a 4-layer technology. Here's the LPF file. We can go in and look at some of the custom elements that got loaded. We have custom libraries that are part of the PDK, and here we have surface mount capacitors, some inductors, various vias that are part of the technology, and we can start adding these to our design. But before we do that, let's go and add another process to our project, and I'm going to go add a generic SiGe process, a GenBIC process, to our module design here. And when I do that, it asks me what I want to do about the layers or the technology files. Here it's asking me if I want to take my GenBIC IC and have that be the dominant integrating or default technology. So we're going to say no, and we're going to keep the module as the dominant technology to integrate with. So let's create a schematic now that we can start designing our IC on. And again, because the environment is hierarchical, this could just represent the top layer of our IC, and we can add various levels of hierarchy as we see fit to make this to make this work. So given that our default technology is the module, how do we associate with this schematic the IC layout technology? Well, to do that, we just go into the schematic and select the options, and rather than using the project defaults, we're going to tell it that we want to use the GenBIC process. We can also give it a Z offset so that when we look at ICs using this technology on the module itself, we can see it relative to its proper height on the module. And ahead of time I figured out that this was going to be about 120 or 1200 microns. So we'll go and do that. And now we can start adding elements to our IC. So you can see here that in addition now to our module library, we've added the GenBIC library. Again, this is done automatically by the environment when we load the entire PDK. And I'm just going to put down one NMOS device, and we'll try to make it fairly large so that it'll be easy to spot at the module level there when we're looking at things. And now we'll go and put down a few ports. So we can make this into a sub-circuit and place it on our module. And we can look at the layout for that, and it's rather large at the IC level, but of course when we put it up at the level of the module, it's going to get fairly small very quickly. Before we do that, let's go put down a capacitor so we can put things into perspective a little bit. That capacitor right there, it asks us, since we're placing things at the module level, and this is the integrating technology, it asks us what stack-up should be used for this element. So we're going to tell it that we want to use the module process. Go and look at the layout. We have our nice little surface mount capacitor there. I'm going to move it up so that 0, 0 will be in this vicinity here, and we'll be hopefully able to see much more easily the IC when we drop the sub-circuit down. So to do that, I'm going to go back to our element palette and go to the sub-circuits and drop our IC on the schematic. And now if we go look at the module layout, you can see down here is our IC. Got placed roughly at the 0, 0. And if we look at that in 3 dimensions, we can see kind of the proper perspective there. Zoom in on this a little bit and expand it. You can see there's our surface mount device, and there's our NMOS devices that we put on the IC, and I can see them in all their detail on the layout. So presumably if I continue to design my my module by going back and forth between the module level and the IC, maybe adding an additional IC technology like a gallium arsenide technology, I can not only co-simulate these at the circuit level, but I can also move things around on the die or on the module to optimize the electrical performance or optimize the manufacturability. I can make real trade-offs not only in the electrical performance but across the whole spectrum of issues in the design. So this is how we would set up a multi-technology project in the AWR design environment. If you have more questions about multi-technology design, you can go back to the website, awrcorp.com, and look at some of the other videos, or you can contact your AWR sales professional.